Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 6, Compiling GPU Programs. In the previous video, you learned the very basics about writing shader code and the code involved in the most basic of all shaders. The next step is to learn how to compile and link the vertex and fragment shaders to create a GPU program. To continue with the goal of creating a reusable framework, you're going to create a utility class that will perform these tasks. But before we start doing that, we'll need to learn about some of the official API-defined functions for OpenGL. We need to use these functions to load and compile the shader code and link those two shaders to create a fully functioning GPU program. The official documentation is maintained by the Kronos group at the reference given here. And before we start coding, we'll talk about the basic functions, again defined by the OpenGL API, and which are provided for us in Python by the PyOpenGL binding. And all the functions that you'll see, they'll have this basic format. The function name will be in bold, the different parameter names will be italicized, and there will be a description beneath that. All right, so first let's talk about the individual shaders. So shader objects must be created to store shader source code. The source code has to be sent to those objects that were created in the GPU, and then the shaders must be compiled. That's 3 different tasks, and each one of those is accomplished with one of the following 3 functions. First, there's GL create shader, and we pass that a parameter corresponding to the type of shader that we're going to make, either GL vertex shader or GL fragment shader. These are constants defined by OpenGL. This function creates an empty shader object, and it's going to be used to store the source code for a shader. This does have a return value, and it's a reference to the shader object. So it doesn't return a shader object, but returns a reference to the shader object. Once we've created a shader with this function, we can then use the function GL shader source, and that takes in 2 parameters. First, the reference of the shader that was created with the GL create shader function, and then the actual code for the shader. And this will be some very long string containing all the code. And what that does is it uploads the code to the object in the GPU. Finally, once the code is uploaded, we'll use the function GL compile shader. And again, it takes as a parameter the reference, which is previously generated with GL create shader. And what that does is it compiles the source code in the shader object referenced by that parameter. So it assumes you've already run the previous function to load the shader code, and then it compiles it for you. One question you might have is, well, what if there happens to be an error in your shader code? And this is one of the difficulties of programming in 2 languages at once. Right? We have our CPU side application, which we're developing with Python, and then we're sending things over to the GPU using GLSL, the shading language, and things are compiled over there. And if there's a problem, the errors don't automatically appear for us. We actually have to query the GPU to find out if any errors happened when compiling the code. And if errors did happen, then we have to retrieve them and display them. And so error checking is accomplished with the following 3 functions. First is the function GL get shader IV, and that returns information from the shader. Again, we reference the shaders by that parameter, and you can retrieve different types of information about that shader, and the type of information that will be retrieved is specified by this constant shader info. And again, it's one of these OpenGL constants. For example, you could determine what type of shader that reference is referring to with GL shader type, but we'll actually be using the constant GL compile status. And that will tell us whether or not compilation was successful. So that'll return a Boolean object for us. And then, if compilation was not successful, then we'll want to get the log of whatever the error messages were. And that's accomplished with this command, gl get shader info log. Again, this assumes that compilation has already taken place, so there will be something in the log to look at. It retrieves the log for the shader, specified by this parameter, shaderref. And again, it'll return some kind of a string, which contains information about the compilation process, such as error messages and warnings. And if the shader didn't compile correctly, might as well clean up the code and delete the shader object. And that can be accomplished with the code gl delete shader. And once again, we have to pass in the reference to the shader object that was created. And this will just free up the memory. We're not always used to doing this depending on the programming language that you use, such as something like Java or Python that does automatic garbage collection for us and frees up memory for unused objects. We need to do that manually, and that's accomplished again with this function, gl delete shader. All right, now that we know about those 6 functions, we're going to go ahead and head over to Sublime Text, and we're going to add on to our graphics framework. We're going to start creating a utility class called OpenGL Utils, which will use these functions to compile some shader code. So let's go ahead and start up the program. I like to use Sublime Text. So let's start that up. All right, and here we are. Again, one of the things I like about Sublime Text is you can see a list of all the different files we've been working on. So we have our core root directory where we're storing all of the code, or we have our main directory and then a subdirectory called core, and that's where we're putting in kind of some of the main application utilities. We have base and input, which we wrote last time, and we're going to add another file to this class. So go ahead and we're going to add something. We're going to add a new file to the core directory. I'm going to go ahead and save this right away. This is going to be named OpenGL Utils. And when I'm naming files, I usually like to start off with a lowercase letter. OpenGL Utils.py. All right, let's go ahead and let's start writing some code. So first, we need to go ahead and get access to some of the contents of the OpenGL library. So we're going to import some things from the OpenGL package. From OpenGL, let's go ahead and import GL, the GL namespace. All right, now this class is going to contain a bunch of static methods. We're not going to have to instantiate an object here. So just as a comment, this is going to contain static methods to load, compile OpenGL shaders. Oops. And link to create GPU programs. All right, so let's call this class OpenGL Utils. We're extending from object. And in order to create static methods in Python, we actually use a kind of a decorator static method before we actually define the function. So I'll def this first one, which will use those 6 functions we just talked about, will be called initialize shader. It'll take in 2 parameters. First, a string containing all the code for the function, call that shader code, and then an OpenGL constant called shader type, and that'll be GL vertex shader or GL fragment shader. All right, so let's go ahead and start writing some code here. First, there's lots of different versions of OpenGL. I'm going to start off by specifying a certain version of OpenGL that we'd like to use. So I'm going to go ahead and specify the OpenGL version we're using and any additional requirements. Let's see, first let's create a string called extension. See, grid extension GL underscore ARB underscore shading underscore language 420 pack. Require that. All right, let's see. So that's a little bit big. Let's see, can I make that a little bit smaller so you can see the whole thing? All right. And then the shader code. For the shader code, I'd like to add something to the beginning. Let's say version 130, then a new line, plus the extension, and plus that string defined right up there, plus the previously existing shader code. There's just some preliminary strings that we'll want tacked on to the front of whatever the shader code is. All right, with that technical stuff out of the way, now it's time to jump into actually using some of the functions. So first, we're going to create an empty shader object and return the reference value. Right, and that's accomplished with, I'll call that shader ref. That'll be the return value if it compiles okay. Right, so I imported GL, and in the GL namespace, that's where all the different functions live. So I'm going to run GL dot lowercase GL create shader according to whatever shader type was specified earlier. And then I need to store source code in the shader. So to do that, we run GL shader source, and using that shader ref that was just generated, and shader code. And finally, we need to compile the source code that's stored in the shader. So GL compile shader, again, referenced by the parameter shader ref. Right. Once again, just in case something doesn't go according to plan, we need to do our own error checking. So next, we're going to go ahead and query whether compilation was successful. Right. To start off, just create a new variable. We'll call it compile success. And so we're going to get the shader information, GL.gl get shader IV. So I need shader ref, and then the constant GL. We want information about its compile status, and if it was not successful, so if we don't have compile success, then we need to retrieve the error message. Error message. And I'll store that in a string. So let's say error message equals GL get shader info log. Whatever that shader is currently storing in its log. And then we'll go ahead and we'll free some memory. That's used to store the shader program. We'll do that with GL delete shader. Now, we could just print out error message, but it returns as a byte string, which is a little bit weird. You'd see like a lowercase b prepended to your string. So I actually want to convert the byte string, which is returned by OpenGL, to a character string. And it's just a little formatting issue. So I want to convert the byte string that's returned to a character string. And to do that, I'll just say error message. And again, this is just for nice formatting. So I'm going to add a new line at the front, and then error message I'm going to decode using UTF-8 format. And then, since there's an error with the code, we probably want to stop the program. So we're going to raise an exception, and which is going to halt the program and print the error message. Right, in order to do that, in Python we just say raise exception. We'll just print whatever that error message is. So if there's some problem with the code, we'll just kind of quit out right there. Now, and that's all if we did not have compile success. Right, an error will be triggered. But if we get to this point, right, compilation was successful, in that case, we just want to return the reference to the shader program. All right, we have a nice compiled shader reference. All right, so when we get into our applications, we're actually going to end up running this little bit of code twice. Once for the vertex shader and once for the fragment shader. So next, we need to learn about the code, which we're going to use, the OpenGL functions, which will take these two shader programs and combine them together to make a working GPU program. So let's head back over here. And again, it's going to seem very analogous to what we talked about before. And there's kind of a nice pattern here. So in working with GPU programs, again, analogous to working with shaders, first, we have to create an empty program object. We do that with GL create program. Right? And this is used to hold shader objects. Just like with creating a shader, it returns a reference that can be used to access this program later on. And so the first step is to create a program, and then we need to attach the shaders. That's accomplished with the function GLAttachShader. Again, we refer to the program by its reference value, and we attach a shader, and we refer to that by its reference value. So this function will attach a shader object to the program object. Again, we'll be doing that twice. And finally, once we've attached both shaders into the program, we want to link them. Right? And again, we just need a reference to the program because the shaders have already been attached. So this will link them together to kind of combine them into a fully functioning unit. It also does some error checking. For example, we recently discussed in and out variables. At this stage, the GPU would check to see if there's an out variable in the vertex shader. There should be a corresponding in variable in the fragment shader. Just making sure that things line up correctly and everything's consistent. All right. So the next step is going to be to check for errors. Again, just like we checked errors in the shader, we're going to check errors in the overall combined program. Right, so let's see, what do we have here? First, we have get program IV. Again, just like for shaders, we need a reference to the program object, and we need a constant, which is going to state what type of information we'd like to retrieve. In particular, we're only going to use this using a constant GL link status to make sure that linking was successful. And if for some reason it's not successful, if this returns some kind of a false value, we can get the log attached to the program, which stores information about the linking process, like errors and warnings. And in that case, again, we probably want to delete it because it's just taking up memory. And that's it. Those are the 6 functions we're going to need to create a program out of the 2 previously compiled shaders. So again, let's go ahead and open back up Sublime Text. So we're still working in the OpenGL utils file. we're going to add a second function on now. Right? And this function is going to use, this new static function in our class, is going to use those 6 OpenGL functions to link together the programs. All right. So let's go ahead and we're going to create a new function, a new static function. I'm going to watch the indentation here. Static method. And we're going to define a new function. This is called initialize program. Right? And the 2 bits of information we're going to need, and this function is going to call the one we created previously. So vertex shader code and fragment shader code. All right. And you might have noticed that since these are all static methods, they don't have the self reference here. Right? They don't require any access to instant-based data. All right, so we're going to go ahead and initialize a program. So to do this, what we're going to do is first compile these 2 shaders and store their references using the program that we just wrote. So we're going to compile shaders and store references. And so first we'll say make the vertex shader reference. And we're gonna run this function we just wrote in OpenGL utils. Remember, it's called initialize shader. And the parameters we need to pass to this, well, we're gonna send along the vertex shader code. And remember, when we initialize a shader, we need to tell OpenGL what kind of a shader it is using one of those constants. This will be gl.gl underscore vertex shader. And then we'll do the exact same thing for the fragment shader. And so this is going to be fragment shader ref. Again, using OpenGL utils, initialize shader. And here we use fragment shader code. And we specify that it's a fragment shader using the constant gl.gl underscore fragment underscore shader. All right, so compiled our shaders. Now we need to create our empty program object. And we do that, we're going to store the reference, call that program ref. Do that with the function gl create program. Right, then we have to attach the previously compiled shaders. And that's accomplished with the functions gl attach shader. Now we have to tell it what program we're attaching to and the reference for the corresponding vertex shader. Then again for the fragment shader. Right, so they're attached. They're already compiled. Now we just have to link those 2 together. And so we'll link the vertex shader to the fragment shader. And we accomplish that with gl.gl link program. Have to pass it that reference to the program. And now we just want to make sure that the linking turned out okay. And so we're going to query if linking was successful. So I'll create a variable to store the Boolean link success. gl.gl get program IV. So we need the program reference and the constant gl link status. And if it didn't work, right, if you do not have link success, well then we're going to retrieve the error message. that in this variable error message, just like last time. If this seems familiar, that's good. gl.get program info log, and that program ref. Let's move that up so you can see it a little bit. All right, so we'll retrieve the error message. We'll free some memory. Use to store the program. gl.gl delete program. Delete by reference. And then, again, if we're going to display the error message, it gets returned as a byte string. It'll look a little bit better if we convert it to a character string. We do that with error message. I like to add a new line to the beginning. So we decode that using UTF-8. And then, again, we're going to raise an exception, which halts the program, and print the error message. And that's going to be just with the code raise exception error message. And just as before, if we do have linking success, then we'll get to this point in the program. Right, so linking was successful. And so we're going to return the program reference in this case. So just return program ref. All right. And this is going to be a really helpful utility class because we definitely don't want to type this in again and again for every single application we have. So the next task, which we'll wait to do in the next video, the next task is going to be to actually compile the shaders from the previous video using the functions we created in this video, because we really want to see that yellow pixel in the middle of the screen. So we'll do that in the next video.